started now. Good morning, everyone. Thank you very much for attending this workshop. We're very much looking forward to presenting our work on biocompute and also listening in to what questions, suggestions, and feedback that you may have with regards to working with the standard. My name is Janisha Patel, and I am the Training and Outreach Lead of the BioCompute Project and an MBA candidate at GW. I would like to thank my team and the rest of the biocompute community that have really made great contributions to this effort. Raja Mazumdar, our principal investigator, Jonathan Keeney, co-investigator, and Hadley King, the operational lead of the project. If you have any questions during the talk, please feel free to type them into the chat box. We have 3 other people from my group who will be looking out to the chat, and we will do our best to address the questions as they come in. We will also be holding a Q&A session following the presentation. Hadley King will be our moderator, and attendees can use the raise hand feature during the Q&A session to ask a question. Please note, this workshop will be recorded, and the recording will be sent to all attendees shortly after. The goals of this session are to introduce biocompute objects for computational analysis for those of you who are unfamiliar with our work, provide biocompute resources for future reference in the way of documentation, and finally to demonstrate the tools available to build biocompute objects via the BioCompute portal and BCODB. Previous biocompute workshops have introduced how BCOs are built using cloud-based platforms such as 7bridges and Hive. So following that, we are now showing the tools available on the BioCompute Objects portal and how they enable interoperability in both research and regulatory review for scientists in the public or private spaces, and especially from the perspective of FDA personnel. I will start with an introduction to biocompute, provide a little bit of background history and the need, and then we'll provide several demos. We'll show how to navigate the BioCompute portal, how to create an account and create, save, and access BCOs. We will also provide a brief description of the database and the schema, as the portal infrastructure could be extended to any company or institution that would like to establish their own private DB using the open source repository and documentation available on GitHub. And finally, we'll provide a brief demo on how the BCO framework is integrated into external platforms by showcasing the BCO transfer mechanism from external resources to the portal via API. The BioCompute Object Standard aims to be inclusive and extendable with a low barrier of entry for researchers looking to communicate a variety of NGS analysis. As you can see here, one application is a regulatory submission of NGS analysis conducted in the clinical trial for HCV-1A. This application addresses how an analysis pipeline can be validated and replicated within a regulatory environment. Another application could be for disease detection. Tuberculosis is a top infectious killer with multiple strains and corresponding resistance. How can we communicate the RE-seq-TB pipeline, which is the sequencing via Illumina HiSeq and the analysis, in a way that allows for replication of lineage identification, prediction of recurrence of TB, and resistance? Another highly relevant research space is vaccine safety. On the right, I have a previewed portion of a BCO that captures a customized algorithm in R. This algorithm was developed by CBER to be used as a safety assessment for aluminum content in vaccines for infants, with the output being aluminum profiles created in the NGS pipeline. Now, this was a slide that was created by Dr. Vahan Simonian, who was at the FDA at the time. Raja and Vahan were discussing the NGS lifecycle around 2012. So this process begins with a sample. That's then used in an experiment, and from the experiment, you do a sequencing run. There's file transfer and archival, there's data retrieval. So there are a lot of steps that go on, but the last steps are just as important as the initial steps. So knowledge extraction from all the data is the key. And most of the time when we're talking about knowledge extraction, we're talking about bioinformatics pipelines, and how these pipelines were run and used is extremely important for FDA reviewers to understand. Because of that, there were a lot of issues coming up at the time, and that's the context in which they were looking at it, in terms of evaluation of products by the FDA. For computational analysis, a lot of good work goes into developing the analysis, tweaking the parameters, testing the pipeline, QCing the results, and so on. For a high quality analysis, this can take a lot of time. And when someone goes to report what was done, often the communication of those pipelines loses some of those granular details. And so often what happens is this leads to the analysis looking like a black box to anyone who is unfamiliar with it. So let's explore how and where the BioCompute framework has the potential to add value through the lens of an antiviral drug candidate. In general, the FDA's guidance documents provide recommendations for submission of next generation nucleotide sequence recommendations for submissions, apologies. For example, the FDA's Division of Antiviral Products would provide recommendations for the submission of next generation nucleotide sequence analysis procedures and data in support of resistance assessments for the development of antiviral drug products. The division then performs independent analyses of all resistance data associated with antiviral drug products being developed. And often the complexity of the data makes it challenging for reviewers to analyze and validate the sequence information for many reasons. Lack of standardized bioinformatic protocols or analysis communicated for analyzing these large data sets, insufficient protocols provided, etc. Now, according to these guidelines, sponsors should submit the appropriate details for the sequencing platform, the protocols used for sample prep, the raw NGS data in FASTQ format, and the methods used to analyze the data. So when a product is submitted to the FDA, it's accompanied by these bioinformatics protocols. And when the FDA reviewers read it, they can find issues, they can have questions, and they can go back to industry and ask, what did you mean by this? You used a particular software, which version did you use? Because we know that version X has a problem and so on. So industry then gets back to the FDA, and the cycle can cost literally millions of dollars because it's not as simple as an email chain. There are protocols in place, which means this communication needs to happen. However, because there are no universal HTS data and data analysis standards, several questions remain. What HTS analysis pipelines are being used? How are these pipelines being validated? What algorithms are being used for specific applications? Is there reproducibility between algorithms? What parameters are used by the sponsor? Now, what if there were already a standard format for industry to submit to FDA, which is understandable by FDA reviewers and accompanied with all the relevant fields that answer these questions? So that's where BioCompute comes in. This BioCompute object can encapsulate all the recommended information that is delineated in the agency's guidelines. A BCO provides transparency needed to allow the FDA to document the exact algorithms, versions, parameters that inform a regulatory decision. Sponsors will be able to submit a BCO that contains all this information required to assess an HTS analysis pipeline and to reproduce the results. Once submitted, this object makes it easy for reviewers to replicate and go ahead and say, yes, this makes sense, we're going to approve the product, or no, we can't approve it because you use some analysis methods which are most probably not giving you correct results, and so on. So this is supposed to save time and money. That's what the major driving force for the BioCompute objects are. And also so FDA reviewers can run those BioCompute objects on their own platform and replicate this analysis. Early discussions to address the challenge of workflow communication began in 2012 at a small scale. And in 2014, the FDA's Genomics Working Group convened a meeting to formally discuss the topic. It was determined the resulting solution to workflow communication should satisfy 4 main criteria. 1, be human readable. 2, be computer readable. Designed to structure information with predefined fields and associated meanings of values. 3, contain enough information to understand the computational pipelines, interpret information, maintain records, and reproduce experiments. And finally, 4, be immutable, designed to ensure the information has not been altered. In collaboration with the FDA, what we came up with was a BioCompute object written in JavaScript object notation, JSON format, is categorized by domains, encourages fair principles, is adaptable, and preserves data provenance, with unique IDs for versioning. Similar to how a meal recipe contains the ingredients, proportions, steps, and kitchen tools needed, and many other details, if the recipe has all of this information, you can exactly reproduce the same dish really well, right? So we understand this about recipes, but we never really followed through with it for bioinformatics. Now, BioCompute is a complete recipe of not only the pipeline flow, but also all the parameters, all the inputs, all the outputs. It's a completely consistent, reproducible piece of standardized information on a recipe. It answers the question, how do you produce this type of computational outcome? Granular reviews of each step in a bioinformatics analysis are necessary, as a lack of reproducibility could have major implications for review. So I'm going to briefly run through the domains that make up a biocompute object. You don't have to read the fine text on the left. Just follow with me on the right-hand side some of the key domains and the questions they answer. Now, how can we track user attribution? Who created this pipeline? Who contributed, reviewed, or authored it? What version is the BCO? Has this BCO been reviewed yet? These questions can all be answered in the provenance domain. Next, it's important to understand why this pipeline has been designed. So we came up with a usability domain. This domain answers the question of how a biocompute object can be used and for what analysis. The person who first develops the BCO has to say, this is how it should be used. It would not make sense to use a biocompute object that, let's say, was used to look at mutations in coronavirus to look for mutations in pox virus. Just like that. One has to modify the pipeline and test to make it work. Now, how does a sponsor communicate additional structured information that may not be defined in the BCO schema? Well, that's what the extension domain is for here. Next, the description domain provides a space where a researcher can communicate any external references. These could be associated PubMed articles or UniProt IDs highly relevant to my pipeline. This domain includes pipeline steps and the relationship of input-output objects. Information in this domain is not used for computation. This domain is meant to capture information that is currently being provided in FDA submissions in journal format. The next question is, what versions of what tools have been used for this pipeline? Because it does matter. As you get different tools and different versions, the answers might be different. And next, that's how we came up with execution domain. What is needed? What algorithmic tools and what software prerequisites are required to execute this analysis? And the next one, how do you parameterize your computation? What are the thresholds? What are the parameters driving your machine? All of this is included in the parametric domain. Now, the input-output domain and the error domains are very important because the object also has this validation concept, which allows you to figure out if your environment is working in the way that it should. So given the input files and the inherent error provided, is the output this analysis claims to have gotten valid? BioCompute is an IEEE approved standard for communicating bioinformatics analysis. IEEE is the Institute for Electrical and Electronics Engineers. We started this process back in early 2018, and we received approval from the IEEE Standards Association in 2020. Below, we have the link to the official standard and the open source repository the IEEE also administers. It's officially known as IEEE 2791-2020, which is a bit of a mouthful, though, so we still call it by BioCompute. This standardization can enable large organizations and government institutions to adopt it, helping a lot with interoperability. All cloud products and tools that provide BCO functionality are conforming to the schema approved in the official standard. Back in July of 2020, the FDA announced support for the use of BioCompute in regulatory submission filings, and the standard was included in the FDA Data Standards Catalog, indicating they will accept BioCompute as part of the submissions of high-throughput sequencing data for 4 different new drug applications to any of the 3 participating centers, which are CBER, CDER, and CIFSAN. It's been accepted by these 3 centers within the FDA, and we're looking to extend adoption by other centers. Several platforms currently have working prototypes for automatically capturing a BCO, including CBER's Hive. 7 Bridges has built in a BCO app to read, write, and export workflows, and DNA Nexus is also working on integrating BCO functionality into its platform. Over the development process, many different groups have helped with the development of BioCompute, both conceptually and technically. A few of them are listed here. probably about 400 or so different individuals have participated in one way or another in helping to develop the technical specification. So now that we've provided an introduction to the BioCompute framework, I'd like to show the resources available for you to better understand the framework and produce your own BCOs. I'll be showing how to navigate the portal and how the portal's BCO builder can be used to record workflows in a structured and secure way. We'll walk through how to create a BCO in the BCO builder together and how to edit that. By the way, there might be a slight lag with my pointer as I give the demos, so I'll try to be extremely clear about what I'm selecting. If there's ever a point at which you'd like me to repeat a step or slow down, please feel free to let me know. So here's the BioCompute portal homepage. On the left-hand side, we have BioCompute documentation available. This includes user guide, best practices, and tutorials. If you'd like to learn more about the standard, we also link out to the IEEE documentation for standard details and working group details. For those interested in the technical development of BCO, you are welcome to join the technical steering committee meetings. Details are on this card on the right-hand side here. So as I mentioned, there are existing tools for BioCompute building. Some are already built into platforms. We have an instance of Galaxy that is up and running on AWS, Amazon Web Services. Galaxy is a very popular open source platform, a workbench, and we have a BioCompute write capability on that. So users are able to build their own pipelines and record the entire analysis as a BioCompute object. We have that ability on Hive, both on the public GW version of Hive and the FDA's version of Hive. So users are able to record an entire pipeline as a BCO there as well. To name a few others that I mentioned earlier, Seven Bridges is a private genomics company that has their own workbench that with a graphical display to wire up your pipeline, and they also have the ability to record workflows in BioCompute objects. And DNA Nexus, a private company that provides a cloud-based data analysis and management platform for DNA sequence data, is also currently working on building in the ability to create and view BioCompute objects on their platform as well. So there are a few platforms that have this ability. And we also have the BCO Builder, an entirely standalone tool. It's a web-based form that you can fill in. It walks the users through each of the domains and fields in a BioCompute object and lets you know which are required. And this is what we'll be walking through building a BCO on today, just to keep it platform agnostic. Now, before we do this, I'd like to show you some key documentation that we provide. For anyone who has no familiarity with what a BCO is or what the domains inside them convey, there's a quick start or a cheat sheet that will provide this information on how to build a BCO. Similar to how when you unpack a box from IKEA, there are easy to follow instructions. And today I will go through how to fill those domains in using the cheat sheet. So this quick start guide can be found on the BioCompute documentation site under quick start and user guide, and provides a new user guide for creating BCOs, quick checks, guidelines, and a high-level view of what information each domain should convey. I'll go through a few of them here. On the left-hand side, we have the 8 top-level domains. We have the execution domain. It's the environment in which the bioinformatic analysis was run. This has platform for information as well as any drivers and prerequisites for that. Resources required to run this workflow are delineated in the external data endpoints nested in the execution domain. The external data endpoints show that when you run this workflow, you need access to XYZ resources. The parametric domain is where all non-default parameters are included. As it is currently written, the standard requires that only parameters that are non-default for that version of the software be included in the BCO. The IO domain, input-output domain, represents the inputs and outputs of the workflows. It's just a list of these files and where to access them. They are not kept on board with the BioCompute object. They are just references to those files. We have the error domain below, is used to evaluate a pipeline's accuracy and precision. It represents the range of outputs that are within a defined tolerance level. It can be used to optimize or verify an algorithm. Now, this consists of 2 subdomains, empirical and algorithmic. These would be false positives, false negatives, minimum detection rates, and so forth. Together, the IO domain and the error domain form the verification kit. So essentially, given a set of input files and the error domain, are the output files valid? A BioCompute object also provides a space for contributors in its provenance domain. So let's say we have a list of contributors and are unsure as to how to describe their type of contribution. Here we see all contribution types options mapped to Prov-O, PAV ontology, provenance, authoring, and versioning. Further details on the ontology can be found by opening the linked article. Right here. Now, how should we version our BCOs? According to the cheat sheet here, BCO versioning should adhere to semantic versioning. Here we see that a major version change would qualify for a new BCO, and therefore it is recommended that the versioning of a BCO only utilize minor and patch, or 2 digits. Further details on semantic versioning can be found by opening the link site here. But to even fill these domains in, you need to start somewhere. As a researcher, you need a template, an easy-to-use tool to build your product. That tool is BCO Builder. First, you need to have an account on the BCO portal. We'll walk through how to register for an account on the portal, how to build an object, save an object, edit a draft, validate your object, and publish. On the top right here, I can see login register, which shows that I'm not logged in. So let's say I just like to browse existing BCOs to get a feel for what the final objects would look like and what information they would convey. Without any credentials or special access, I'm able to view published BCOs here on the BioCompute Objects tab on the menu bar. Here are the published objects in the database. BCO Builder also works without being logged in. Users are able to build a BCO and download to your local machine, but that's the only function you can do without being logged in. To publish to the BCO to the portal DB, you first need an account. And to create an account, click Login Register on the menu bar. I'll include a link to this in the chat box if you'd like to follow along yourself. So to create an account, first click Login Register on the menu bar, then go to Sign Up here, and fill in the information and click Sign Up for Portal. User. So a message comes up alerting you that the account on the portal was created and requesting that you activate your email for the DB account. An activation email is sent immediately after registration, and users won't be able to access the DB server if they don't activate their account first. So I'll take a moment on a separate screen to activate my newly created account. Now that I'm logged in, we can see the top menu bar has changed. I now have access to account information. I'm able to modify my details, fill in my affiliation. You can see that I have, you see that I have access to the BCODB server because I activated that through my activation email. This means I now have a server to publish BCOs to. So now I'll log out and log back in. So we can see the information has been saved in the database, my affiliation details. And going into Builder, I'll just go ahead and fill in a couple of fields. We've got name, workshop demo, version 1.0, and license. The default or recommended license can be Creative Commons Attribution 4.0, identified as https spdx.org. I'll just copy and paste that license here. This would let others distribute, remix, tweak, and build on my work. Now, if I'd like to save my work, I'd click the Saving and Publishing dialog here. I can see here there are instructions on the left-hand side to indicate what each of the buttons are for. The only functions available initially are validating and downloading. If I attempt to validate, the system will respond with an error message, as the majority of required fields that are marked in red below are not filled in. I can, however, still create and save as draft. So if I'd like to save the BCO as a draft, I'd have to first select a server to save it to. From the dropdown, I'll select the server and click Create New Draft. I can see here that creating drafts was a success. If I return to the BioCompute Objects page, I should see my new object saved as a draft. And I see that right here. I can return back to the builder by clicking on it and selecting the BCO accession and clicking, and I can modify my draft here. So how would I go about filling this BioCompute object out? If I didn't know what to fill in the provenance domain, each domain does link out to its specific documentation. So with the name, now you fill in the name of a BCO, which will describe the workflow. So for this example, I'd like to record the safety assessment performed for aluminum content in vaccines for infants using the customized algorithm in R developed by CBER. Now, this is the use case I mentioned earlier in the presentation. In the name, I'd put BCO Workshop or Demo. Now, version, what exactly am I supposed to put in here? If unsure, users can click on the header of the domain with the info button. Let's say this is the first time I'm recording this analysis as a BCO. So the version would be 1.0. The usability domain. This is a plain text field used to describe the purpose of the pipeline, the biological question, or what was trying to be done here, and so forth. I'd like to use the space to communicate where the algorithm used was originally developed, why it was developed, and what the algorithm does. The description domain includes things like keywords and cross-references in addition to pipeline steps. My keywords here would be safety assessments, aluminum, infant, vaccine, anything that would aid in the searchability for this object. I can also include any PubMed IDs of relevant or associated articles here by adding an external reference. So for the sake of time, I'm going to show what this would look like completely fleshed out. Give me a moment now. Okay, so as you can see, the information has been filled in the domains of the BCO. So here we have the IO domain. The IO domain represents the inputs and outputs of the workflow. It's just a list of input and output files and where to access them. They are not kept on board with the BioCompute object. They are just references to those files. Then we have the execution domain. It's the environment in which the bioinformatics analysis was run. This has platform information as well as any drivers and prerequisites required for that. So the script driver for this BCO would be R, and the software prerequisites would be the version of R. The external data endpoints show that when you run this workflow, you need access to these two resources. Resources required to run this workflow are delineated here in the external data endpoints and can be added. As I mentioned earlier, in the description domain, these keywords are selected to aid in searchability for this object. Here we see a list of steps and detailed descriptions of each. This pipeline has 6 steps. Next is the parametric domain, where all non-default parameters are outlined. Given that there are no parameters here, we can assume that this analysis follows all default parameters. So let's say I'm at a point where I filled out all the required domains. The next step would be saving my progress on this BCO. I'd click Saving and Publishing dialog, and I'd save as current draft. Now, since it's already been created, this BCO will save on the server I originally selected when saving my draft. I'm unable to change that. I would have to create a new draft if I'd like to save to an alternate server. Now, if I return to the BioCompute Objects page and retrieve my object, I should see that my edits were saved. So now that I want to publish the BCO, the first thing I have to do is validate the draft, because the draft cannot be published until it's been validated. I'd click Validate, and I see here I have a return message saying BCO is valid. So if I click Publish Draft now, I'll receive a success response and will be redirected to the published object. There are several ways that I can view my published BCO. I can view in color-coded, tree, and raw. In the color-coded option, I can selectively choose which domains I'd like to view. I can remove and add them as I need. In the tree version, I can expand and collapse domains. And here we have the raw JSON. So next we'll talk a little bit about the DB and the schema. So the BioCompute schema is kept, as I mentioned, in an open source repository on GitLab.
I'm sorry to butt in, but we have a question.
Okay.
Omar asked if you can edit the raw JSON or color-coded modes, and I just wanted to touch on that right now. So what Janisha was demonstrating most recently was for the published object view. So a published object is immutable and cannot be edited. If an object is still in the draft phase, so you would be able to access it via the builder. So Janisha was showing the BioCompute object viewer, which is where you see published objects. The builder is where you can modify objects. And yes, the color-coded method Janisha was modifying on the page, but we do also have in the builder a tree view and a raw JSON view, which are in test for being for having modifications. So within the next month or two, with our next release, we'll have those features live on the public site.
Thank you, Natalie. So the BioCompute schema is kept, as I mentioned, in an open source repository on GitLab. We can access this from the portal, IEEE documentation, and open source right here. I'll walk us through that. I've included a URL on this slide deck here that you will have access to after the presentation. So I can access this by going to the IEEE card on the dashboard, scrolling down, and selecting IEEE SA Open Source Project. Now, we start with the 2791 object.json, and below that, you'll see that all the other domains have their own associated files that are cross-referenced, so you can go down and pick out any one of them that you're interested in to learn more about it and see what the schema says. So returning to the dashboard, if I scroll down to the bottom of my portal page, I'll see here the BioCompute portal is a user interface. It's designed to be independent of the BCODB. Anyone or organization can set up their own instance of the database, BCODB, behind their firewall. Now, there are 3 different repositories to support this project. Right on the bottom of the page here, we have Portal, which is the front-end user interface. We have BCODB, which can be used completely independently of the others. And we have Portal User DB, which supports the login and user management of the front end. Each is independently versioned and has its own associated documentation. As you saw, these all link to their specific GitHub repositories. Now, documentation on how to set up an instance of the BCOD database can be found on BCODB repository. This was done to support those who wish to maintain their own data in their own safe spaces and not have objects in a public space. So let's say that I work as a researcher for Children's National, and I'm handling sequences that are associated with human clinical trial data that are required to keep confidential. For security, Children's has set up their own instance of the database behind a firewall using those instructions on the GitHub repository. Right? So there's an instance of BCODB that resides behind the Children's National Firewall. And I, as a researcher at Children's, want to access that BCODB from Portal to publish my BCOs directly to the organization's DB. I would first need to be provided credentials by the Children's BCODB administrator. Okay, so to demonstrate this, I'll first act in the role of the administrator. For the demo purposes, I am behind the GW firewall, and I'm using the GW's instance of BCODB here. So as admin, I would log in, I'd go to my account, and I would see my BioCompute object servers here. I have a host name and I have a token. I would provide these 2 credentials, host name and token, to the individual in my organization that would like to publish to this database. Okay, so I'm copying and pasting these 2. Now, as the researcher, I'd log into my own portal. I'd go to my account, go to add server. I take that public host name and that token that I just copied. Sorry, we're having a bit of technical difficulties right now. Give me just one moment.
Is it an issue with the VPN, Janisha, or?
No, I'm logged into VPN.
Okay.
Hadley, feel free to fill the silence with answering questions if you'd like.
Yeah. Okay. So I'll take that. Peju and Sinqui. I'm so sorry about that. I probably butchered both of those. They asked about permissions and sharing, and in the um, current version, we the sharing of objects is handled by the groups that folks are associated with, and we have it's set so that all users are assigned to a group by default. We have not implemented the creation of new groups and the management of users within those groups in this version, but like the other question, that is in our roadmap for our next release. So the way that works is that somebody who creates an object will decide which group they are has permissions for that object, and then the membership to that group is assigned by the group owner, and the folks in that group can view or edit the object, much like group permissions on any Unix-based machine or other platforms. Um, and what, as far as sponsors being able to access data, that would fall into the same place. So the functionality that Janisha is attempting to demonstrate right now, where you are able to use the portal to access multiple versions or multiple instances of the database, would be one of the ways that we see this going on. So, okay. So I'll let Janisha continue with the demo, but assuming that, there was a sponsor submission from USA Pharmaceuticals, USA Pharmaceuticals would create their own instance of a database because they want to manage the firewall and how folks can access it. And they could potentially provide that information, or they could provide accounts to external people who could then access it. All right, I'll turn this back over to Janisha.
So this is actually a case of user error. I noticed that I kept a space after I copied the public host name into its field. There was a space, and because of that, it wasn't fetching the server information. Now I can see the server information has been fetched, and then I scroll down to add server. Now the correct functionality would be that my organization's DB server would be added, and I could then access it to view the BCOs that reside there or publish my own BCOs to that server. So I see that I now have two servers, my organization's here and my own. Now, if I go to BioCompute objects, I should see the list would reflect objects from both servers. And I use the source column for that here. So this is my organization's BCOs. These are in my portal. So individuals have the ability to transfer from alternative platforms or local machines through the API access and code provided on Swagger. This next section will be primarily geared for platform developers to aid researchers to pull, submit, and analyze BCO objects without going through the user interface. So similar to downloading sequences from NCBI using eUtils, a bioinformatician could pull or create BCOs without using the user interface, using the commands outlined here in the Swagger documentation. So this is the Swagger site for API access. And let's say I create a BCO in a text editor on my local machine, and I'd like that BCO recorded in this DB. Using the Swagger site for API access and my specific token provided to me on my portal account page, I would authorize to export data from my local space to the portal. So this is a preview of the BCO API documentation page, and it has all of the available API calls grouped by the type of call: account management, group management, and BCO management. You'll notice here above there is a locking mechanism on the right-hand side next to each bar. This indicates whether you are authorized with credentials, and for a lot of these processes, you have to have authorization. To retrieve your token, users would need to have created an account in Portal and go to Account page, and under Servers, copy token. So I have my token right here. That's my authentication for the BCO API. I've copied my token, and now I should go back to the API Swagger page and click on the authorize with the lock.
And just as a caveat, the token is the only credential that's required to access a user's account or their privileges. So it's not something that you want to share or publicize, which is why Janisha and I are using demo users and for this demonstration. So don't share your token; keep it private.
Okay, so I entered my token here in the Swagger site. And now that I'm logged in using my token, I can actually try out all of the API calls on this page. So let's say I'd like to see which groups that I have permission for on this BCODB server. I would use this describe call. And if I scroll up to account management and do API/accounts/describe, click here, I'll see the description and parameters here. If I click on try out, the blue bar appears here for execute, and it will give me the curl command from which I can run from terminal or be formatted into other programmatic languages. I get the curl command, which includes my token, authentication, and all the required headers. It gives the URL that I would need to use to make this call, and then it shows the response below. As you can see in the response body, here we've got the user object for the API for Janisha herself, and it's listing here what the different groups are. So under BCO Publisher, I have these permissions to add a BCO, change a BCO, delete a BCO, draft a BCO, publish, and view. There are 3 groups listed here: BCO Drafter, BCO Publisher, and my user group. If I go back to my account on the portal page, I can see that these are the 3 groups that I have access to right here. Now, if I'd like to create a BCO in BCODB using the API, I can use the create call. I'd go back to the API calls, scroll down to the BCO management, API, objects, drafts, and create. This is the API call to create a BCO draft to submit to the portal. You can see here we have an example format where it says data. There's the model and example values table that is displaying the model right now, which is kind of provides the schema definition. If you click on example value here, it will give a box where you can manually enter information. So we're going to click try it out to submit a BCO here. Prefix is BCO, and the user group will be my personal user group that I found before here. I don't need to provide an object ID because we are creating a new BCO, so I will be deleting this line. The schema is IEEE. And for the contents, we're going to paste the BCO that I've created in a text editor here. Now we're all set to submit our object. I clicked execute and I can see I get the curl request with the status code that it was accepted and the object was submitted. In the response, we're provided a message and we're given the object ID that was just created. Now, if I go back to the portal and look for that object under drafts, I should be able to see it. And this object is called API_demo. So I have here, I'm in the portal and under BioCompute objects, scroll down and I have the draft of the API_demo that we created using the API Swagger site. So to recap, this site is for external platforms such as Seven Bridges, DNA Nexus, and Hive to look at what the API calls for and how they'd like to interact with the database. It provides a means for which external platforms can transfer their partially completed or finished BCOs into the BCODB. This would allow for partially completed BCOs to be imported into the database and be completed in the portal. Each BCODB comes with its own Swagger site, fully integrated, and has documentation for developers and administrators. And Hadley will walk through what this looks like with importing BCOs from the Galaxy platform.
Okay, so to recap what you said about the Swagger site, just really just to provide documentation for folks who want to use the direct API calls as opposed to using the web interface. And the real value is that by trying it out, you get these curl commands, which are command line interface. If I copy this into a terminal and hit enter, then I get the same response back in JSON that we see from this command here. So to do any of the operations listed in our API documentation, you can just build the commands using this interface if you don't know how to just build them straight out, and then enter them into a command line and get the responses you desire. Now, as Janisha said, our main goal with providing the Swagger documentation was to enable others to interact with the BioCompute database and to use the tools we've developed rather than every single platform coming up with their own way to create and manage a BioCompute object. We have this documentation here and these methods here for them to interact with what we've developed so far. So one of the examples, or the main example that I'm going to talk through here, is with the Galaxy project. This is, well, I'll show you on GitHub. Galaxy, Galaxy is an open source platform. And as such, they allow contributions from the Galaxy community. Right here is an example of the pull request for the functionality that I'm going to display here. The reason I'm showing this is because it's still in draft and needs a little bit of review, but I have it running on my local machine here. So hopefully within the next month or so, this will be live on the newest releases for Galaxy. So Galaxy has the concept of a workflow, which is a set of tools strung together to give you a specific result. In their workflow editor, you can see workflows that you have present, or you can upload, import workflows from other folks. And they have a lot of annotation that is associated with their workflows. So I don't know if you saw when I was on that page, there's this annotation section here, which is where you provide a summary for your workflow. And this one I'm showing here is really just a simple one I put together for troubleshooting and creating BioCompute functionality. It's just, it takes a sequence input, a session number, downloads that file from NCBI, creates in silico reads from that file, grooms the FASTQ files, then aligns the in silico files to the original sequence and gives an output. So a little circular, but goes through a lot of very common NGS processes. So, and Galaxy also allows you to provide annotation for each of the individual steps, as well as annotation for the whole workflow. So under, okay, so the workflow is a set of tools that can be strung together. What there's also the concept of workflow invocations, which is a specific instance of a particular workflow. So the way that BioCompute works is it's supposed to represent a specific instance of a computational pipeline. So the entry point for BioCompute with Galaxy is at the workflow stage. So this can be accessed from either there's a way to access it from the workflow menu if you run a workflow. And I'm going to do this one here because, like I said, this is a very quick and very short workflow. It takes about 2 or 3 minutes to run. So downloads a file from NCBI and then starts to do the alignment. Now the functionality that is actually already present in Galaxy versions that are published now is the downloading of a BioCompute object. Now I don't want to do this while it's actually in the process of completing the workflow because it won't be complete. There'll be missing sections. Obviously, this jobs that have not completed yet. But you can see we are almost done here. 2 out of 7 jobs. So here, I just got a power notice. I need to plug in. There. So once this is done, you can select a particular invocation, and you see these are the 2 that I had 13 days ago, 20 hours ago, and then a few seconds ago. This one's still working. But for one that has completed already, we expand the BioCompute, and you can download the object, and it gives you a raw JSON that is created from the Galaxy workflow. So you get your input list, all of your steps. I want to point out that we have the input and output files for each of these. The prerequisites list a specific Galaxy tool that's resolvable through the tool shed. And then the usability domain right here is the workflow annotation taken from the summary. So there are some sections that are not complete. There isn't a place to put keywords, and there's a couple pieces in the execution domain that need to be filled in. But assuming that you ran a Galaxy invocation and you wanted to export this to the portal, you would go and use your API key. You need the base URL. So what is the URL for the database? The base one. You need to enter a prefix, and I'm going to do Galaxy here. And then you want to do a username. So I'm going to take my username and enter that. And then you hit submit. And I got an error message here. Token provided does not have draft permission for prefix Galaxy. That's because Galaxy does not exist as a prefix on the BCO portal. So I did that on purpose to show there is some error handling functionality. But if I put in BCO, which does exist as a prefix, because we have BCO publisher and drafters, and hit submit, I get the object was submitted. It gives me the object ID and all of that. So I can go back to the object listing, drafts, and we can see here, created just now, Galaxy BioCompute Object Development Test. And then clicking on this, you can see that the information that it pulled from Galaxy is here in the portal. A good part of the BioCompute object has already been completed, but some of it still needs to be filled in. And then you can go through the rest of the process of publishing, validating, saving that Janisha has already demonstrated. And like I said, I used Galaxy because I have had some familiarity with Galaxy, but we see this as something that this process could be replicated across many different platforms. I do see a question here about converting existing Galaxy workflows to BioCompute objects. So I'm not exactly sure. Okay, there are a couple of different ways I can answer that question. I think what I'm going to say first is that the BioCompute is generated from a Galaxy invocation. So if you have a Galaxy invocation in your history as a user, then you can use that to export a BioCompute object. So I don't think that it's not workflow dependent. It is invocation dependent. So if you have an old workflow and you want to create a BioCompute object from that, you can simply just rerun the workflow and then generate a BioCompute from that invocation if you don't have an invocation already in your history or list of invocations for that. Happy to clarify if that doesn't make sense, but yeah.
Okay, awesome. So before we open it up for Q&A, I'd like to take a moment to acknowledge all the individuals who have contributed to BioCompute from the FDA, University of Miami, Seven Bridges, DNA Nexus, and the BCO community members who have truly advanced this framework into the standard it is today. This work was done by myself, Janisha Patel, and Hadley King, the technical lead, was integral to BCO portal development. I'd also like to thank Dr. Jonathan Keeney, Assistant Research Professor and BioCompute Lead, and Raja Mazumdar, my PI at the George Washington University. And if you have any questions, please feel free to contact any one of us. Just a reminder that the presentation slides and recording will be shared to all attendees after the presentation. And sometimes it can be a bit difficult to follow along in a live demo, especially if there are user errors that can break the flow of the demo. So if you'd like to revisit specific sections of our presentation, I'll be including the YouTube links on this next slide here. Okay, so we'll move into the Q&A session if you'd like to place questions in the chat box or just raise your hand using WebEx reactions. And if no questions come to mind right now, please feel free to email any one of us.
Do you want to show the contact us on the portal page? Actually, that might be good.
Sure, yeah.
So there at the bottom of the BioCompute object portal, where Janisha showed the GitHub links, there's also a contact us link and and the links to the GitHub. Using the links to the GitHub, you we are happy to respond to any issues or questions somebody might want to submit. Um, so the report issue on GitHub button there on the bottom bar will get you started on either a feature request or a bug report. So they kind of walk you through how to fill that in. And then there's also, if you go back to the portal page, there's also a contact us form, which once this form is filled out, it will send a Slack message to the BioCompute team. So we'll all see that and be able to respond to your question. Looks like there's one more question about using CLI to record BCO. Um, and to answer that, there has been a couple of different attempts at that. I think that they are present in the BioCompute GitHub organization. One of them, I know that there are two repositories that were experimenting with that. I don't. They were projects done by other students or other graduate researchers. So they're still, they're in project phase. I wouldn't say they're ready for production, but that would be a good place to start if you were interested in trying to pick it up. There's also a tool that was built by somebody who was one of our Seven Bridges collaborators at the time for using R to catalog the parts of a biocompute, or it's an R Shiny app to create a biocompute from an R script. And I think one of the submissions to the Precision FDA Challenge was using a command line logger to also populate parts of the biocompute's parts of a biocompute object. That can be found in the Precision FDA GitHub. All of those submissions were made public. I can throw a couple of those into the chat now. Let me. There's, unless there any other questions. All right. Well.
Thank you very much, you guys. I really appreciate your time today. If you have any questions, feel free to reach out. I will also be sending over the slides and recording of this workshop in an email shortly.